And today we hope to have Vasily Krylov from Harvard, I believe, Higgs and Coulomb branches and geometry and representation theory. Oh, please.
Yes,
Well,
thank you. Thank you very much. Thank you very much for the invitation. It's a great
yeah.
pleasure to give a talk. So let me start with the plan for the three talks. First one will be sort of more introductory. Um, so first of all, let me introduce some notations. Namely, when I talk about gauge theories, they are always a quiver gauge theories. So the starting point will be a quiver that I denote by Q. And please interrupt me and ask questions if something is not clear. So we have a quiver. So we have a quiver Q, and it has some vertices that I denote by, like, we have some vertex like this, and we put some numbers, associate them to vertices. I denote them by V1 and V2. And we also form the framed quiver, meaning then that for each vertex of the original quiver, we associate to it an additional quiver, additional vertex. And we put some numbers there and we draw arrows like this. Okay? I denote the framed quiver like this. So we have the data of framed quiver. So we have Q heart and we have this V and W. And now to these data, we can associate a group that I denote by G. And in this case, it's just the product of GLV1 and GLV2. In general, just the product of GLVIs. In particular, this group does not depend on the choice of W's, of framing nodes. And we also associate a representation of this group that I denote by N. And this will be more or less literally the representation space of the framed quiver. So in this case, it's given by this formula. Okay. Any questions so far? So start with the quiver, consider V and W, construct group and representation of this group. And in physics, this group G is called gauge group, and the representation N is called matter. And whenever you have such a pair of reductive group acting on some finite dimensional representation, there are two interesting varieties that one can associate to this pair. And one of them I denote by MH, and this is so-called Higgs branch. And the other I denote by MC, and this is so-called Coulomb branch. And I should say that both of them are affine Poisson varieties. And they are Higgs and Coulomb branches of certain theories associated to this pair G and M. And in some sense, these two varieties should be considered dual. Dual in this 3D mirror symmetry sense or in symplectic duality sense. Sometimes people call them symplectic dual. And I will explain what this means during the talk. So for now, we just like have these two different structures, and maybe let me just mention like what types of structure appears on both sides. So on the left-hand side, this Higgs branch is something relatively classical, namely for these quiver theories, it's nothing else but Nakajima quiver varieties. And they have, and being more careful, the Nakajima quiver varieties are certain resolutions of these Higgs branches. So they are non-singular, symplectic. And these MH are affine and Poisson. And these Nakajima quiver varieties, they have interesting enumerative geometry. like quantum D module, some curve counts from P1 to this Nakajima variety, and so on. So there is some very interesting geometry in them. And on the dual side, these Coulomb branches, they're not so classical. They were defined by Braverman, Finkelberg, Nakajima. Of course, again, following predictions of different physicists. And they have a very interesting representation theory. Again, being more careful, I should talk about quantizations of algebras of functions on these Coulomb branches. And this representation theory has to do with Yangians and more general quantum groups. And 3D mirror symmetry somehow relates these two different structures, enumerative geometry on one side and representation theory on the other side, like roughly speaking. And my plan for today will be so the first talk, I will just discuss the Coulomb branches. So this will be more like introductory talk. And during the second talk, I will discuss a certain concrete conjecture, so-called quantum Hikita conjecture, that predicts a relation between left-hand side and right-hand side, that establishes some 3D mirror symmetry statement. And during the third talk, I will explain some concrete applications to representation theory of quantum groups and Yangians. So any questions so far? That's the general plan. Today we will concentrate on Coulomb branches. I believe that the Nakajima varieties is something more or less familiar, so I will speak about the right-hand side, about Coulomb branches. And hopefully even today I will be able to illustrate like why they are useful, even to understand some purely algebraic questions. Okay, if no questions, then let me explain who are these Coulomb branches. So I will denote them like this. They depend on the choice of reductive group and representation. And let me start with the simplest possible situation, namely when our group G is just a torus and the representation is just a trivial one. In this case, it's very easy. The Coulomb branch will be just like in this case, it will be symplectic, just T star to T check, where check just means a dual torus. So it's just the product of the Lie algebra of this torus and T check. But it's useful even in this situation to give a slightly more fancier version of this definition. Namely, what we want to say that functions on the Coulomb branch is equivariant Borel-Moore homology of the affine Grassmannian for the torus T, and the product structure is given by some convolution product that naturally exists on this space.
So do you assume that people familiar with this convolution construction or what?
Right. So I will say yes. Of course, I'm not assuming, but one picture to have in mind, I think, is the following. So this affine Grassmannian of a group G is some affine version of flag variety. Actually, of some parabolic version of the flag variety, but still, that I will denote by B. And it's like more or less standard story when we want to define the convolution product on equivariant B equivariant homology of G mod B, right? That you can also identify with G equivariant homology of the product of B cross B. And then we have convolution product here, right? Because on B cross B, it's like a matrix algebra. We can take products. And about this story, one should think very similarly. But I will say how this convolution works explicitly in this, because in this example of the Fine-Grassmannian of a torus, it's very, very explicit. And then I will sort of explain how to extract this convolution product for arbitrary Coulomb range from this simplest possible example.
So here T can be any dimension torus.
Absolutely, absolutely. Yes, T is arbitrary.
And N here really means a zero-dimensional representation, right?
Say it again?
N is the zero-dimensional representation.
Yes, it's just zero. Yes, zero-dimensional
Yeah. So
representation.
there's only one single point. Thank you.
Absolutely. Yes. So let me remind you who is the affine Grassmannian of a torus. By the very definition, this is T of Z modulo T of double bracket Z. And that's just the lattice lambda. So that's just a discrete space where lambda is the space of co-characters of our torus, space of homes from C star to T. Because T is just C star to some power R. So that will be Z to the power R. So what we're doing here, we're doing something very, very simple. Namely, we're just considering equivariant homology of the discrete space. And definitely what we get at the level of vector spaces, we will just get span over these functions on the torus. That's nothing else but equivariant cohomology of a point. Equivariant cohomology of a point. And these are just the fundamental classes of the points of our lattice. And the claim is that this convolution product in this case is very, very simple. Namely, it's just compatible with the lattice structure. So when you multiply, you just sum the corresponding lambdas and the corresponding co-characters. And that's the reason why you are getting, in this case, you are getting T star to T chat. So this will be coordinates on the torus, and these are coordinates on the Lie algebra. Okay?
So the parameter homology, which is the algebra over the coordinate algebra of the Lie algebra of the torus in this case, right?
This is always an algebra, so it's Borel-Moore homology, so it's always an algebra over equivariant cohomology of, in particular, what I'm using, that it's an algebra of over equivariant cohomology of a point. You can always do this pairing.
But I don't see how the function algebra of the algebra of T is part.
Right. So that you can identify this with functions on the torus, right? And now what you can do...
Then you added some more variables, depends on the rank. Or something am I missing?
Yeah, let me put it more carefully. So it's of course, our object is a module over this thing, but it also contains identities. So here we have class of Z to the power 0. So we can embed equivariant. Maybe I should just write that like this thing as a vector space is just a direct sum over all lambdas in lambda of equivariant homologies of one point, right? Because it's just a disjoint union of points. And each of them, if you want, you can identify with equivariant cohomology of a point acting on the fundamental class of Z lambda. So we get this description. Just a free module over functions on the torus with bases labeled by elements of our lattice. Does that make sense?
Well, because here the N is also consists of one single point. So I guess here is the homology and cohomology.
It's important that we're dealing with homology. N is just zero, so we ignore. So N does not play a role at all.
It's always a point. N is always a single point in this case.
Yes, and lambda, it's important that we're considering homology here, but not cohomology, because spaces are infinite dimensional. So you should think about homology here is like a limit over these lambdas. You see, I'm writing here plus, not a product. Yeah, and every piece is just a free module of rank. Every piece in this decomposition is just a free module of rank 1 over equivariant cohomology of a point, generated by the fundamental class of the corresponding lattice element.
So maybe we move on, because
Yes,
it's kind of very
let's move on.
basic things.
Yes. So now let's see how things work for arbitrary reductive groups. So now let's G be any reductive group, and let's N still be 0. Then, similarly to the previous definition, we define this Coulomb branch again as equivariant homology, but now of the affine Grassmannian of G. Now it's an interesting space. It's just a discrete set of points with the convolution product on it. And let me recall again that the affine Grassmannian is defined as for the torus case, and it can be written as a disjoint union of G of double bracket Z orbits of the points Z lambda, where lambda is an arbitrary dominant co-weight, and these orbits are so-called Schubert varieties, open Schubert varieties. They are all finite dimensional spaces. So affine Grassmannian is an in scheme. Let me maybe put it here. G is a limit of finite dimensional varieties that are closures of this Schubert. Now, that are these Schubert varieties for different lambdas. And this equivariant homology is defined as a limit of equivariant homologies of Gur lambda bars. And yes, there is some multiplication that comes from the convolution, but now let me explain for you how to think about this multiplication. So definitely G equivariant homology of Gur G can be identified with T equivariant homology, and then you take W invariance, where W is a Weil group for G, Weil group. And then we have a localization theorem that allows us to do the following. So we have a torus, I denoted by T. So now T is a maximal torus inside G. And it acts naturally on the affine Grassmannian just by left multiplications. And the fixed points under the action of this torus can be identified with the affine Grassmannians of T that we considered before. And we have a closed embedding, iota. And this closed embedding induces a push-forward map from Borel-Moore homology that we considered before, right? So this is the torus case, and I just add W invariance, and that's the case of G, functions on the Coulomb branch for G. And the claim is that this map is actually homomorphism of algebras. And moreover, just by localization theorem, we know that after we tensor by the field of fractions, it becomes an isomorphism. So, in other words, equivariant homology of the affine Grassmannian that we want to understand as an algebra just embeds inside some localization of the equivariant homology of a torus. And we just discussed the algebra structure here, and this map is a homomorphism of algebras. So in principle, the algebra structure in the torus case determines uniquely the algebra structure here. And that's how people sometimes make some computations, actually. They do localization theorem and they compute something here where things are really. Any questions so far?
So you take equivariant homology with respect to the finite dimensional group. Yeah.
That's right. So actually, usually what people do, but that becomes relevant only if you upgrade to some like actual coherent sheaves, like category 5. So usually maybe in BFN they write homology and here they put G of Z of G, but note that like as vector spaces are just the same because the kernel is pro-unipotent. So
and the convolution, which is a priori defined on the upper homology group, it descends to homotopy equivalent group or whatever.
that's right. So when you define convolution, you define it here, but then you use that you have this identification.
All right. Mm-hmm.
Absolutely, yes. Thank you. Yeah, please feel free to interrupt me with questions. Okay, and now the final step, arbitrary G, arbitrary representation. So in this case, the Coulomb range will be equivariant homology of some space R, so-called BFN space. And let me briefly explain this space. So the first step here would be the following. We construct the space T that is the induced representation. So we take G of Z, product with N of Z over G of double bracket Z. And then we are considering some closed subspace here, that is this BFN space, consisting of pairs G and N, such that if you apply G to N, in principle, if you take an element here and take a pair G and N, after you apply G to N, you only know that you get something that lives here. So BFN space precisely consists of pairs such that we actually end up in N of double bracket, square bracket Z. Okay, and then again, how to think about the multiplication structure on our Coulomb range. It works as follows. So we have this space R, it embeds inside this T, is some closed embedding, and we also have a projection to the affine Grassmannian. Remember that this T is just the associated bundle, so we can just like forget about the second coordinate, about this one, and get a map to G. Remember that G is just this quotient, and that will give us N of Z bundle, some like infinite dimensional affine bundle. And this diagram then gives us a map. So first we start with functions on the Coulomb range that we want to understand as an algebra. Then we can do a push forward, get an element here, and then the pullback for this affine fibration, it just induces an isomorphism. So this thing can be identified with this thing, and composing, we get an injective map, and the claim is that this map is actually an embedding of algebras. So again, we see that after you like did some formal procedure of defining the algebra structure here, then you can always extract this algebra structure from the one without matter. For n equal to
Especially in your title, there is the word geometry. So affine Grassmannian geometrically, it's some vector bundle. Well, for GLN, it's vector bundles, G bundles on the formal disk plus choice of trivialization on the punctured disk. So for this space R.
Yes, absolutely. Yes, there is a. So let me. Yes, so how one should think about this. First of all, yes, for literally for this space R, there is a geometric interpretation. So remember that the affine Grassmannian is moduli space of bundles P on D. This is a G bundle together with the choice of a trivialization P on D without, sorry, and D is a spectrum of C of Z. And here we fix trivialization, trivial on D without 0. So that's the moduli space description of just ordinary affine Grassmannian. And now this space of R, so we still have a data of a bundle, we still have a trivialization, and now we have an additional thing, maybe let me call it S. So S will be a section of the associated bundle. So we take P cross G with N, right? So this is now a vector bundle over D, vector bundle, and S will be a global section of this vector bundle. And if we just do this, then we will get this space T that we had before, this one. And now this condition that G dot N lives in this N of Z, you can reformulate it as follows. You can take your phi, your trivialization, and you can apply it to S, I don't know, 0, namely to, maybe let me put, to like restriction of S to D without 0. And the condition is that this thing extends to a section of the trivial bundle, again, induced N. Does that? So in other words, you should think about the, yes, alternative way is to think that like you had a vector bundle P on D, and you also had a trivial vector bundle on the same D. Now using trivialization phi, we can glue them to one bundle, I don't know, P tilde, that lives over this like Riviola space, that is D cross D over D without 0. And then this condition on S precisely tells us that S defines a section of this P tilde cross G N. So if we bundle over this Riviola space, it glues a section. Okay.
So you want the cohomology. I understand that kind of to think of it, you want to embed it to something which is easily understood. But if I work just with homology of this BFN space, the convolution, is it straightforward, or you need some kind of regularization?
It's more or less straightforward after you. So maybe let me write another way of thinking about this. If you like just play with these spaces a little bit, you will see that this thing that we are doing here, so we're taking, now let me be, let me do G of Z, covariant homology of this space R. Then you can identify this thing with G of double round bracket Z, equivariant homology just of T cross T over N of Z. And so like, or like in terms of stacks, this should be homology of N of Z modulo G of Z cross itself over N of Z modulo G of Z. So what I'm trying to say is that both of these formulas it's easy to convince yourself that there should be a convolution product on this thing, because we're taking a product of two same, like the Steinberg variety story.
Modulo the fact that your stack seems to be of infinite types.
Absolutely, and that's yes, and that's so. This doesn't make sense. This doesn't make sense, and that's the reason why BFN do this. But then, like always, when you want to try to do convolution, you just imitate the definition that you would do here, and just reformulate in terms of the left-hand side, which makes sense.
Okay.
Okay, so that's that was the Coulomb branch, and there are various modifications of this construction. Let me just mention them. Namely, whenever we have some torus F that acts on N and commutes with G, then we can consider the same equivariant homology, but add F into the picture. And then we will get some algebra over equivariant cohomology of a point, that is functions on the Lie algebra of our torus. So we'll get some deformation of our variety.
F, it's what physicists called flavor.
Absolutely. Yes, absolutely. This is a flavor. There are also Fi parameters. They will appear next time. Yes, these are flavor parameters. And another important structure that we have is there is another action, namely we have a C star that acts on our space R, and the action of this guy corresponds to like so-called loop rotation action. So Z goes to TZ, like the coordinate on this formal puncture disk that we had. And you can also add this T star to the equivariance, and then what you would get, you will not get a commutative algebra, you will get a quantization of our Coulomb branch algebra, I denoted by A. Namely, you get some associative algebra, again over equivariant cohomology of a point that we identify with C of H bar. So for H bar equal to 0, you get functions on the Coulomb branch, Poisson commutative algebra. For H bar equal to 1, you get something non-commutative.
And so your quantization is always non-formal, yeah? Because
absolutely, absolutely, yes. Okay, and finally, what I wanted to mention is that one can replace cohomology for me it will be K-theory, namely when instead of considering Borel-Moore homology, you can consider equivariant K-theory of the same space R, that is K0 of the category of equivariant sheaves on our BFN space. And similarly, we can also do G cross C star, equivariant K-theory, and in this way, we will get what I will denote by MC cross and AC cross. So these are like multiplicative version of the Coulomb branch. That's
so I'm a bit confused. So when you spoke about homology, yes, it's homotopy invariance, replacement of one group to another one, that's okay. When you speak about coherent sheaves, your R is kind of in scheme.
right.
So then equivariant either I believe no, but still, is there a problem with the definition of the G equivariant coherent sheaves? Because G of O, G of Z orbits, yeah, that's kind of, they're finite dimensional. G orbits are not.
That's right. That's right. So yeah, let me be let me be careful here. Let me write. You can still do with G, but yeah, not to confuse, because yeah, that's not a problem. And in any case, when you categorify this thing, you do consider. Now it becomes important that you're considering G of Z covariant objects, but not G. But yeah, but what I was trying to say is that yes, you're right, but it's still, since this like GER lambda it's still an affine vibration over G mod P lambda, something finite dimensional. So it's still true that G equivariant K theory.
But this affine spaces are infinite dimensional.
This one already finite dimensional.
Finite. Okay. Good.
So the point is that when you define your thing,
yeah.
you always define it as a limit of K theory of something finite dimension.
Okay, great.
That's yes. That's and know that here it was very important that I was doing like coherent shifts, not vector bundles. Right? It's like homology, not cohomology.
Okay.
Any other questions?
I do have a question. So here, the Coulomb branch was defined with the function algebra being more homology of the von Grassmannian. So the convolution product in general is the commutativity obvious or well known or doesn't matter?
Sorry, say it again.
The algebra, you do have an algebra structure with the convolution product, but the commutativity, is that always commutative, or you're doing probably the commutativity is not important here?
It's not obvious. It's not obvious that what you get will be commutative. So this thing will be commutative, and one like cheap way of doing this is by using these localization things that I explained. Like this multiplicative Coulomb branch when G is just a torus and n is 0. In this case, this MC cross will be just T cross T check. And that's something that you can very easily compute. And then since the algebra structure on arbitrary Coulomb range can be extracted from the one for this thing, then it's commutative. But there's also a more like canonical way of proving this.
Thank you.
Okay. Now let me explain one important piece of structure that we have. Again, that comes for free whenever you consider this Coulomb branch construction, namely the integrable system. So remember that our algebra is this, and we can also consider equivariant cohomology of a point, and we can embed it inside our algebra just by like acting on one. And this will give us a Poisson commutative subalgebra inside the Coulomb branch algebra. And like at the level of varieties, we will get a map from the Coulomb branch to T mod W. So that's just the spectrum of this equivariant cohomology. And again, just like this localization type results, they tell you that generic fibers of this map are tori, and this is an integrable system. So the dimension of this space is half of the dimension of this space.
And they degenerate over what?
Over some collection of hyperplanes. So actually, again, like this Coulomb branch story is nice because you can always say precisely. So you have your Lie algebra G, and it has some roots alpha that are elements of T dual, and our representation space it has some weights. Weights, they are also elements of T dual, and these roots and weights they define as some hyperplanes here. Like hyperplanes. And the claim is that whenever you're outside of all of these hyperplanes, then the fiber will be T-check.
And monodromy monodromy about these hyperplanes, it's probably can be described, quite explicit.
But that's so everything happens over complex numbers, so they are like codimension, like real codimension 2.
Yeah.
So yeah, from that perspective.
For example, point on the line has real codimension 2.
Yes.
It does not prevent the
Yes.
Bundle with regular connection
Yes,
has a
yes,
monodromy.
yes,
So that's
yes.
okay. So then the question still makes sense, yeah.
Right. Yeah, I don't know the answer. Yeah.
Okay.
Maybe I can just say that indeed, that's just localization theorem. You can actually describe all of these fibers. Namely, if you consider a fiber over some x here, then like you this is some mcx here, and functions on this, maybe I don't know, let me call it pi, and this will be pre-image of x, and functions on this pre-image will be equal to, so we take G-equivalent homology of our space R, and then we specialize to X. So by localization theorem, what we get same homology. Now we take centralizer of this element X, and you see if X is generic, you indeed just get a torus. And then you should take fixed points of your R with respect to X. And then what you see is that the pair centralizer of Gx Rx, that's just like Rx is just the same space of triples, but are now associated to the group centralizer of X and X invariants. So in some sense, like you can like fiber, like in some sense, this Coulomb range, they have this factorization property that like if you take a fiber, you get again fiber over zero, but for the Coulomb range for the smaller group and smaller representation.
Yes.
Okay, and now let me explain the relation to quantum groups. That's like one reason why people who are doing some algebraic stuff are interested in these Coulomb branches. So now let Q be an ADE Dynkin quiver. So before we could consider arbitrary quiver, now I want to consider some particular quiver. And remember that we had these V's and W's, and they determine for us lambda and mu. And lambda will be the sum of Wi omega I, and mu will be lambda minus the sum of Vi alpha I. Where now we consider both of them as weights of GQ. So now we take the Lie algebra corresponding to the quiver Q. It has nothing to do with the gauge group. And omega I are fundamental weights, and alpha I are simple roots for this Lie algebra. And now, whenever you have some weight, you can associate to it so-called mu shifted Yangian. And this shifted Yangian is the following structure. It's very similar to ordinary like Greenfield Yangian. Maybe I should say specify that this is like corresponding to this Lie algebra GQ. It will be generated by E's, F's, and H's. And these are some like loop versions of ordinary CR generators, because you see we have this additional index K and S here. And K should be greater than 0, and S should be greater than minus the pairing of mu with alpha I. So that's the place where this shift appears in this story. The labelings for H's depend on mu, on this shift. And then you mod out by some relations, and relations are literally the same as for usual Greenfield Yangian. And in particular, all of these H's commute with each other.
And Greenfield Yangian, is it a special case of this construction?
Absolutely, yes. So if you take zero shift, so if you just take Y0 of GQ, you will get Greenfield's new presentation of the Yangian. And you see that this literally corresponds to this pairing being equal to 0.
Then next question is, you see, conventionally with Greenfield Yangian, it's whatever, it's quantization of some Lie algebra. So there is this. Okay, so what one should modify it in order to get a shifted?
Yeah, very good question. Very good question. We will get to this like in a couple minutes, I think.
Okay.
So indeed, but with one caveat. So even if you think about the Drinfeld Yangian, there are two filtrations on this Yangian. So one of them, maybe more standard, is the one that recovers for you u of GQ of t. But there is another filtration that recovers for you something commutative Poisson, so more like classical
I
linear.
understand, but it's already in Drinfeld's paper that any quantum enveloping algebra can be thought of quantization enveloping algebra or quantization of
Absolutely.
functions on the Poisson lead law.
Absolutely.
And this
And
is
we will present a generalization. I will explain the generalization of this story.
you quantized algebra of functions, quantize the ideal, which truncates this. Okay, and then you just quotient. Okay, yeah, I think I understand. Okay, go ahead.
Okay, great. And yeah, let me just mention that the shifted Yangian, there is also a multiplicative version of this object defined by Finkelberg and Cymbaluk. That is some shifted version of the quantum affine group associated to GQ. Okay, and now let me explain the relation with Coulomb branches. So the theorem due to BFN, Kamnitzer, Kadera, Webster, Weeks, Finkelberg, Cymbaluk, and Varniola-Vissarot, different parts of the results, claims that actually this shifted Yangian always, so the Coulomb branch that we discussed before is always a quotient of the shifted Yangian, y mu of GQ. And this map is compatible with this integrable system that we had before. Namely, here we had the subalgebra generated by H's, and it literally surjects onto this integrable system that was a covariant cohomology of a point.
And mu, no other restriction on mu, because Coulomb branch, by the notation, you see lambda and mu is arbitrary.
Absolutely, yes. So the choice of lambda and mu is like just a different way of presenting a choice of v and w. And because we put no restrictions on v and w, so yeah, lambda and mu are also arbitrary. So in other words, if you think that like you have these large Yangians and they have they have different quotients being these Coulomb branch algebras that are already.
Maybe you explain it later, but Drinfeld Yangian is after all a Hopf algebra, yeah.
Right.
And since you mod out by some ideal, it does not look as a Hopf algebra.
So actually, that's very, very interesting. I will definitely mention this to some extent later. So indeed, first of all, this Hopf algebra structure in this story becomes kind of interesting because it messes different mu's. So you have a co-multiplication, but now it doesn't go from one y mu to itself tensor itself. It goes to y mu1 tensor y mu2 whenever mu is a sum of mu1 plus mu2. So in other words, the right thing to do is to consider all of these Yangians and their representation theory together, simultaneously. And this follows from the results of Alex, Weeks, and collaborators that actually, yes, this co-multiplication descends to these truncations. So it descends to a c lambda. So yes, there is a very interesting Hopf type algebra structure. This co-multiplication is a bit weird because, for example, it's not co-associative in general, but it's very, very important and useful. We will discuss this.
Yeah.
Okay, right, and in particular, since we have these surjective maps from the shifted Yangians to our Coulomb branches, we get some purely algebraic description of these Coulomb branches. They will be isomorphic to so-called lambda truncated shifted Yangians. So these are certain quotients of our Y mu's, and let me be careful here. So these quotients, they also depend on collection of parameters R. R lives in C to the power sum of WI's. You should think about them as like evaluation parameters. In Coulomb branch story, this corresponds to these flavor parameters, to this deformation. So actually you have a family of algebras that are all quotients of the same large Yangian. And same with quantum groups, with parameters being multiplicative. Okay, so now let me explain how it works in classical limit. So that's precisely your part of your question, at least. Namely, remember that we have these quotients from shifted Yangian to this like Coulomb branch algebra. And then BFM actually prove that this realization of the Coulomb branch as a quotient has a very nice natural classical limit. Namely, that the Coulomb branch is isomorphic to what's sometimes called generalized slice and affine Grassmannian. So that's some space that is defined as follows. You consider the intersection of two spaces. One of them is denoted by W mu. I will explain it in a second. And the other is some closed space, closure of some. Oh, and I forgot Z. Sorry. Should put Z everywhere. So now we live inside this infinite dimensional space. Let me again emphasize that now the group we're dealing with is the one corresponding to the quiver Q, no gauge group at all. And now in this space, we're considering the intersection of two things. And one of them, this W mu, it's the following structure. So as a space, it's just literally a product of the following things. It's like a Gauss type decomposition, but with mu shift in it. So you take upper triangular matrices in Z inverse, and one here corresponds to the fact that you want the value at infinity of this matrix to be just identity. And same thing with T and with U minus. And the shift mu appears here. You just multiply by Z mu. And definitely we have natural coordinates on all of these spaces. Like on the first one, we have E coordinates, H coordinates, and F coordinates. So these are literally the classic limits of, so this Y mu is just the classic limit of this shifted Yangian. And then when we intersect with this closed subspace, this literally corresponds to passing to quotienting by some ideal here that we had here. So again, the upshot is that this is basically just infinite dimensional affine space. And then we put some closed conditions and we get an interesting finite dimensional variety out of it. That is this Coulomb branch. Okay, any questions? Okay, since I wanted to work out this example carefully, but since I don't have much time, maybe let me just tell you the answer. Because, I mean, this definition maybe looks a bit hard to work with, but actually it's quite explicit and nice. So let me just formulate the answer in the following example. Like, who is this Coulomb branch? How to think about it explicitly. So we are considering just A1 quiver and we put V and W in it. And then if you just like unravel this definition, you will see the following answer. You will see that this Coulomb branch is just, in this case, just consists of 2 by 2 matrices that I denote like this. with entries being polynomials in Z, such that the degree of x12 and x21 is less than V. So that's our V. And x22 starts with Z to the power V plus some lower terms. And the determinant of this matrix is Z to the power W. So that's the only place where the W appears. And let's see how that works explicitly, how this definition works. So, for example, if V is 1, then x22 must be x minus a. The conditions on the degrees of x12 and x21 tell us that both of them are just numbers, just some constants. And then this determinant condition forces us to put x11 to be equal to this thing. And divisibility of this one by this one implies that a to the power b plus bc must be equal to 0. So in other words, we just see the Kleinian singularity in this case. This Coulomb branch is just a Kleinian singularity. If w is greater than or equal than 1. And if w is 0, we will see t star to c star. And another example is if w is equal to 0, then the determinant of our matrix must be equal to 1. And so this just means that the only condition is that we have two polynomials such that one starts with zv, degree of the other is less than v, and these polynomials are coprime. And this is nothing else but the moduli space of maps from P1 to P1 with fixed degree. And the Poisson structure that we get from this Coulomb branch story on this space is something that was considered like in 80s. Okay, any questions about these examples? Okay, then maybe let me skip representation theory because I will just explain this next time. That's not a problem at all. In any case, I will use this representation theory next time. So let me just finish by mentioning like one reason why this Coulomb branch approach sometimes helped to resolve some purely algebraic questions. Namely, one question that one might ask is there a way to compare this truncated shifted Yangian and truncated shifted quantum group? And it turns out that the realization with Coulomb branches helps, and it helps to answer the similar question for an arbitrary quiver, and get this comparison just in like by substituting Q being AGE quiver. So I just wanted to mention this. So that's our result with Ilya Dumansky, claiming that for arbitrary pair of G and N, there is always an isomorphism. So of course, like you have some multiplicative version, some additive version of the algebra. They cannot be literally the same, but one might hope that they become the same after appropriate completions at like 0 and 1, and that's indeed what happens. So if you take the completion of the Coulomb branch algebra at 1 as a module over like this integrable system thing, then it will be naturally isomorphic to the completion of the additive Coulomb branch at 0. And this isomorphism is compatible with all of these localization theorems that we discussed before. In particular, the corresponding algebraic objects are also isomorphic. And the argument here is purely geometrical. You use the Chern character type isomorphism applied to this BFN space of triple, which is infinite dimensional, so you should be careful here. Okay, so let me stop here.
Okay, thank you very much. Questions?
Yeah, I have a quick question. Does it make sense to ask which side of 3D mirror symmetry this was on? Was this the B side?
Actually, that's so. Of course, yeah. So from my actually secret. So yeah, let me put it this way. If I understand correctly, everything that I will be talking about happens on one side. So I'm speaking about this 3D dual or symplectic dual thing that like we have two spaces, but effectively I think that all the what. So yeah, let me maybe put it this way. But again, if definitely we might have people in the audience who know understand this much better than I do, because I'm not a physicist at all.
Are there physicists in the audience?
I don't know. Yes, but yeah. So in the general prediction is that we have this GN. They define for us some quantum field theory that is conformal, not topological. And then this quantum field theory, it has two twists. I will call them F Coulomb and F Higgs that are already topological. And for me, they are determined by the following property, that if you take this Fc, the Coulomb twist, and evaluate it on this Riviola space, on this D cross D over D circle, then you will get functions on the Coulomb branch algebra. And if you evaluate this F Higgs on the same product, then you get functions on the Higgs branch. So I think that what I will be talking about, it always happens something about, it's always about this theory FC. In particular, at some point, there will be some results. So like, yeah, very, very vaguely. So whenever you have something like this, now you can ask yourself the following question. Okay, and what if we evaluate this theory on something, so still on something two-dimensional, so that we still get, so yeah, I forgot to say that both of them are 3D theories. So being evaluated on two-dimensional manifold, they should give us vector spaces. And that's one example of a vector space that isn't actually, it has an algebra structure. But now we can evaluate it on, for example, on P1. And what you get in this case, you should get a vector space, but it should actually be a module over, or this algebra, or maybe quantized version of this algebra. And so what I will be talking about, like, so this space is already has to do with computing some homology of the modular space of maps from P1 to this resolved Higgs branch, some critical actually, and so on. And yeah, so we will discuss some representation theory of this algebra, and the representations we will be getting are of this sort. So you should think about them as like values, very, 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 very vaguely, values of this theory of some different manifolds. But yeah, I will never like consider this theory. So yes, that's about one twist. The one which has functions on the Coulomb branch as a value on this radiolo space.
I see. Thank you.
So 3D mirror symmetry interchanges Coulomb branch and Higgs branch. That's different from 2D slightly. And it's rather they're always hypercalars.
Yes, that's different from 2D. For example, already just because the dimensions of this MH and MC, they are very, very different. So, for example, T star to Pn minus 1 is 3D dual to A2, to this Kleinian singularity, A2 mod Z mod NZ.
So in the categories involved, maybe that's very general question. The categories involved, they are not something like, at least they do not look a priori as Fukaya and DB Koch of some. That's kind of, they both look like
Right.
DB Koch.
Yes, they look so what I will be talking might be related to, but yeah, I would say no. There is an example of 2D mirror symmetry statement for Coulomb branches that is like that's the that were the ideals of Aganagich, and then now there are a couple papers about that of Aganagich and her collaborators. They consider something different than 3D mirror symmetry. Namely, they propose that the Coulomb branch MC I was talking about and the multiplicative version MC cross, where you replace homology by K-theory, that these two things should be 2D dual. In the sense that here you should consider some DB Koch, and here you should consider some Fukaya type category, some wrapped Fukaya type category with some potential. Yes, so that's another story about the same varieties, and that's precisely why I think that what I'm talking about, it's just about one theory, just about like.
More questions? By the way, either elliptic analog you took kind of usual cohomology or K-theory. There are many other, several at least one more possibility to take. Does it make sense?
That should make sense, and there are even people working on this. I mean, I only aware of Artem Prihodko, Nikolai, and Ivan. So there are yes, some people are working on this. Yes, yes. Hopefully, these elliptic Coulomb branches will appear soon.
Okay. All right, thank you. May I ask you actually send me also the notes with your updated notes?
Sure.
Yeah, all right. Okay, thank you, and we'll see you in 2 days on Wednesday, same time.
Thank you. Okay.
Thank you very much. Bye.
Bye.